Right now, while you're watching this video, something is moving through a region of space so distant that sunlight is little more than a bright star. It is carrying memories from a world that humanity had never seen up close until just a few years ago. It is not orbiting a planet. It is not returning home. It was built before smartphones dominated everyday life, before streaming became normal, before Pluto was even classified the way it is today. At this very moment, it is traveling at roughly 14 kilometers every second, fast enough to cross the continental United States in less than 8 minutes, if it could somehow fly through Earth's atmosphere. And what it accomplished changed something much bigger than one distant world. It changed how scientists think planets form. It changed how they think ice behaves in the outer solar system. It even changed how they think entire planetary systems evolve. The researchers who analyzed its data did not describe Pluto as merely interesting. Many called the discoveries astonishing. Others admitted that long-standing assumptions had simply been wrong. This is the story of NASA's New Horizons mission. And here is the part the headlines rarely tell you. It is not just what New Horizons found. It is what those discoveries mean for every frozen world we have not visited yet, including thousands that may exist around other stars. It is what New Horizons is still doing right now, years after its most famous encounter. And it is what will happen to the spacecraft decades from now, long after most of today's missions have ended. Stay with me, because by the time this is over, you will never think about Pluto, or the edge of our solar system, the same way again. To understand why New Horizons mattered so much, you have to go back long before the spacecraft existed, back to an observatory in Arizona. The year was 1930. A 24-year-old assistant astronomer named Clyde Tombaugh spent his days doing one of the most repetitive jobs imaginable, night after night. He compared enormous photographic plates of the sky. One image, then another, then another. Most of the stars never moved. That was exactly what he expected. The work demanded patience more than inspiration. Imagine searching through millions of tiny dots, looking for one that had shifted by only a fraction of a millimeter. It was less like making a discovery, and more like proofreading the same page thousands of times. Then, in February 1930, one tiny point of light refused to stay still. Tombaugh had discovered a new world. It would become known as Pluto. For decades, Pluto remained mysterious. Even the largest telescopes on Earth saw it as little more than a blurry circle. Imagine trying to identify someone's face from the opposite side of a football stadium using a single pixel. That was Pluto. Scientists estimated its size. They estimated its brightness. They estimated its surface. But almost everything remained an educated guess. As telescopes improved, the picture became slightly clearer. In 1978, astronomers discovered Pluto's largest moon, Charon. That discovery helped researchers calculate Pluto's mass much more accurately. Then came another surprise. Beginning in the early 1990s, astronomers started finding many more icy objects beyond Neptune. One after another, then dozens, then hundreds. Today we know there are thousands. This vast region became known as the Kuiper Belt. Suddenly, Pluto no longer looked unique. Instead, it appeared to be one member of an enormous family. That realization eventually led to one of astronomy's most famous debates. What exactly counts as a planet? In 2006, the International Astronomical Union introduced a new formal definition. Pluto no longer met every requirement. Its official classification changed from planet to dwarf planet. The public reaction was enormous. But inside the scientific community, another thought quickly replaced the debate. If Pluto represented an entirely new population of worlds, someone needed to visit it. The problem was obvious. No spacecraft had ever traveled there. None had even been designed to. The farther you travel from the sun, the weaker sunlight becomes. By the time you reach Pluto's average distance, sunlight is roughly 1,600 times weaker than it is at Earth. Imagine replacing the bright noon sun with something that feels more like deep twilight. Solar panels become impractical. Temperatures fall toward hundreds of degrees below freezing. Radio signals take hours to travel one way. Every engineering decision becomes harder. Yet scientists kept asking the same question. What is Pluto really like? Not the blurry Pluto, the real Pluto. Then one scientist refused to let the idea disappear. His name was Alan Stern, a planetary scientist with a simple argument. Humanity had explored every classical planet. Only Pluto remained completely unknown. Again and again, Mission proposals were drafted. Again and again, many were cancelled. Budgets changed. Priorities shifted. Years passed. Some researchers worried the opportunity would disappear forever. Because planetary alignment matters. Launch too late, and the journey becomes much longer. Eventually, NASA approved a mission. Construction began. Engineers faced a challenge, unlike almost any before it. The spacecraft had to survive nearly a decade of travel, operate perfectly after years of silence, then complete its entire primary mission during a single flyby lasting only hours. No second chances, no orbit insertion, no repair mission, just one opportunity. Everything depended on getting that single encounter exactly right. On January 19, 2006, New Horizons lifted off aboard an Atlas V rocket from Cape Canaveral. It left Earth faster than any spacecraft had ever departed at launch. Its speed relative to Earth exceeded 16 kilometers per second. Imagine traveling from New York to Los Angeles in about 4 minutes. That is the kind of speed required simply to begin chasing Pluto. Even then, the destination remained unimaginably far away. The spacecraft would travel for more than 9 years before reaching its primary target. 9 years. During that time, children entered elementary school, finished high school, entire technologies appeared and disappeared. Meanwhile, New Horizons kept flying, quietly, reliably. Every command sent from Earth needed patience. Radio signals travel at the speed of light, fast by everyday standards, painfully slow across billions of kilometers. By the time New Horizons approached Pluto in 2015, a command sent from Earth required about 4.5 hours to arrive. Another 4.5 hours before confirmation returned. Nearly 9 hours for a single conversation. Imagine asking someone one question and waiting almost an entire workday for the answer. That delay meant controllers could not fly the spacecraft in real time. New Horizons had to fly itself. Every observation, every camera movement, every instrument sequence, every backup plan had already been programmed months before arrival, because once the encounter started, human beings could only watch. They could no longer intervene, and that created one of the greatest moments of suspense in the history of robotic space exploration, because New Horizons was about to do something Voyager never could. The surprises did not stop with Sputnik Planitia. As higher-resolution images continued arriving over the next several months, scientists noticed something that seemed almost backwards. Mountains. Not small hills. Entire mountain ranges. Some rose 3 to 4 kilometers above the surrounding terrain. That is comparable to many major mountain ranges on Earth. But there was a problem. Pluto is extraordinarily cold. At average surface temperatures of around -230 degrees Celsius, the familiar water ice you know from a freezer behaves very differently. On Earth, water ice is fragile. You can crack it with your foot. You can chip it with a shovel. On Pluto, water ice becomes as hard as solid rock. Think of the ice cubes in your drink. Now imagine they had the strength of granite. That is the kind of material these mountains are made from. The softer ices, nitrogen, methane, and carbon monoxide, cannot support towering cliffs for long. They slowly deform under their own weight. Water ice can. So New Horizons revealed an extraordinary landscape. The bright plains were made mostly of softer, more mobile nitrogen ice. The rugged mountain ranges stood above them like bedrock. Except the bedrock was frozen water. Researchers believe some of these mountains may have been carried, or partially surrounded, by moving nitrogen ice over immense periods of time. Imagine enormous rocky islands floating inside a slow-moving sea. Now replace the sea with frozen nitrogen. That is not exactly what happened, but it is one useful way to picture the interaction between Pluto's hard and soft ices. Again, everything depended on the flyby in 2015. From Earth, none of this could be seen directly. Pluto had appeared almost featureless. New Horizons showed a landscape every bit as varied as many worlds much closer to the Sun. Scientists had expected a frozen sphere. Instead, they found plains, cliffs, faults, mountain ranges, and evidence that Pluto had remained surprisingly active long after many researchers expected it to become geologically quiet. Exactly how long that activity has continued remains an active area of research. Then came another surprise. Not on the surface, above it. Before the flyby, scientists already knew Pluto possessed a thin atmosphere, mostly nitrogen, with smaller amounts of methane and carbon monoxide. But nobody expected what New Horizons actually photographed. A blue haze. That sounds ordinary. Earth has a blue sky. So does Neptune. Why should Pluto be different? The answer lies in distance. Remember one of our signature numbers. By the time sunlight reaches Pluto, it is roughly 1,600 times weaker than it is at Earth. Despite that faint sunlight, the atmosphere was doing something remarkable. Sunlight interacts with methane high above Pluto. That sunlight breaks methane molecules apart. Those fragments combine into larger, more complex compounds. They continue reacting, growing, changing. Eventually, they become extremely tiny particles suspended in the atmosphere. Scientists often call these particles tholins. They are not living material. They are complex organic compounds, created through chemistry. As sunlight passes through those tiny particles, blue wavelengths scatter more efficiently toward the spacecraft's cameras. The result? A delicate blue haze surrounding one of the coldest known worlds in the solar system. Imagine seeing blue smoke around a campfire. Only this smoke extends for hundreds of kilometers above Pluto. Layer after layer. New Horizons observed multiple haze layers stacked high above the surface, like thin sheets of fog. Researchers are still studying exactly how those layers form and remain so organized. Several models explain much of the behavior, but important details remain uncertain. That uncertainty matters, because similar chemistry may occur on other icy worlds, and perhaps on planets orbiting distant stars. One spacecraft, one flyby, a completely new laboratory for atmospheric science. One feature continued puzzling researchers more than almost any other. Sputnik Planitia. Not just because it is smooth, not just because it is active. Because of where it sits, its location appears closely linked to Pluto's largest moon, Charon. The two worlds always keep the same face toward one another. Much like Earth's moon always shows us the same hemisphere. Sputnik Planitia lies very close to the point facing away from Charon. That may not be a coincidence. Many planetary scientists think Sputnik Planitia began as an enormous impact basin. A collision excavated a huge depression. Later, volatile ices accumulated inside it. Nitrogen ice is denser than Pluto's atmosphere, but less dense than water ice beneath. Over time, the weight of those deposits may have altered Pluto's orientation. Imagine placing a heavy magnet on one side of a spinning basketball. Eventually, the basketball tends to rotate until the extra weight settles into a more stable position. Planetary scientists call this process true polar wander. The entire outer shell slowly reorients. Not overnight, not in centuries. Over immense geological timescales. Some researchers suggest that a subsurface ocean could have made this reorientation easier. Others continue testing different explanations. The evidence is intriguing, but researchers still cannot say with complete confidence exactly how Pluto reached its present orientation. That distinction matters. Good science separates strong evidence from confirmed fact. New Horizons provided the observations. Scientists are still refining the explanation. That is how exploration works. Every answer opens another question. By the time the complete dataset began arriving on Earth, one conclusion became impossible to ignore. Nearly every simple picture scientists had before 2015 had to be revised. Pluto was not merely a frozen leftover from the solar system's formation. It possessed active geology, flowing nitrogen ice, towering mountains of water ice, layered atmospheric hazes, complex seasonal cycles, unexpected chemistry, and a surface that continued changing over geological time. Remember our signature numbers. 9 years to get there. 4.5 hours for one radio signal. Sunlight 1,600 times weaker than it is on Earth. Those numbers are more than engineering facts. They explain why these discoveries took so long. For decades, humanity simply did not have the tools to see Pluto clearly. New Horizons changed that forever. But remarkably, Pluto was not the end of the mission. It was only the beginning of the next chapter, because after doing something Voyager never could, New Horizons kept going, into a region where no spacecraft had ever explored up close. Most missions end after reaching their primary destination. New Horizons did not. After the Pluto flyby in July 2015, mission planners searched for another object that the spacecraft could still reach with its limited remaining fuel. Using observations from the Hubble Space Telescope, astronomers identified a tiny Kuiper Belt object that lay close enough to New Horizons' trajectory. Its official designation was 2014 MU69. Today, it is better known as Arakoth, a name provided with the consent of the Powhatan and related Algonquian peoples. The target was extraordinarily small, only about 36 kilometers across. Compared with Pluto, it was tiny. Compared with a city, it was enormous. Yet before New Horizons arrived, no spacecraft had ever examined such an ancient object up close. On January 1, 2019, after another 3.5 years of travel, New Horizons flew past Arakoth. What it found surprised researchers again. Instead of a shattered pile of debris, Arakoth looked like two rounded lobes, gently joined together, almost like two snowballs pressed softly into one another. Scientists call this a contact binary. The shape matters because it tells a story. Those two pieces probably formed separately, then drifted together at extremely low speed. Not a violent collision. More like two soap bubbles touching. Imagine dropping two marshmallows onto a pillow. They settle together without breaking apart. That is the scale of gentleness scientists believe may have built Arakoth. This finding supported a long-standing idea about how some of the earliest building blocks of planets formed. Instead of countless high-speed impacts dominating the beginning, some objects may have grown through much calmer accumulation inside the young solar system. Researchers continue studying exactly how common this process was. But New Horizons delivered the first close-up evidence from one remarkably well-preserved example. Once again, a single flyby had rewritten part of the story. Why was Arakoth so important? Because unlike planets, it appears to have changed very little since the solar system formed, about 4.5 billion years ago. Earth constantly reshapes itself. Mountains rise. Oceans erode coastlines. Volcanoes erupt. Continents drift. Even the moon records billions of years of impacts. Arakoth experienced far less change. It preserved information from an era we can never observe directly. Imagine finding a sealed box buried since the construction of the oldest city on Earth. Now imagine that box remained almost untouched for billions of years, instead of thousands. That is what Arakoth represents to planetary scientists. New Horizons observed smooth surfaces, subtle layering, unexpectedly few large impact craters, and a surprisingly reddish color caused by complex organic compounds, altered by radiation over immense spans of time. Researchers also found no evidence that Arakoth had been violently disrupted after it formed. That matters, because it suggests parts of the Kuiper Belt may preserve ancient conditions far better than previously believed. The object became something more than another distant rock. It became a record, a surviving page from the solar system's earliest history, and only New Horizons could have read it. Voyager never traveled through this region. No other spacecraft had reached this type of object. New Horizons opened an entirely new chapter in planetary exploration. Many people assume New Horizons completed its work after Pluto. That is not true. The spacecraft is still operating. It continues moving deeper into the Kuiper Belt. Engineers periodically wake instruments, collect observations, measure charged particles, study dust, and investigate the environment far beyond Neptune. Every new measurement helps scientists understand a region that remains only lightly explored. Think about Earth's oceans. Even after centuries of navigation, new discoveries still appear. The outer solar system is far less explored than any ocean on Earth. In many ways, we have barely begun. New Horizons also contributes to studies beyond planets. By observing distant stars from a unique location, the spacecraft has helped researchers make measurements that are difficult from Earth's neighborhood. Scientists continue looking for opportunities to use the mission while power and fuel remain available. There is no guarantee another close flyby target will be found. Suitable objects are extremely rare. The spacecraft has only limited fuel remaining for trajectory changes. Researchers continue searching, but they also acknowledge the challenge honestly. Some questions remain unanswered. Some opportunities may never appear. That uncertainty is part of exploration. Not every mission finishes with one final dramatic discovery. Sometimes, its greatest contribution is continuing to collect careful measurements from a place no one else has reached. Eventually, every spacecraft reaches its limits. New Horizons is powered not by sunlight, but by a radioisotope thermoelectric generator, often called an RTG. Instead of solar panels, it converts heat released through the natural decay of plutonium-238 into electricity. The system produces less power as the years pass. Slowly, predictably, Mission engineers carefully manage every available watt. Imagine running an entire scientific observatory on roughly the power used by a few traditional household light bulbs. Every instrument matters. Every heater matters. Every transmission matters. At some point in the 2030s, available electrical power is expected to become too limited to continue operating the spacecraft's scientific instruments in their current way. Exactly when depends on engineering decisions and the health of the spacecraft. When that day comes, New Horizons will become silent. Not because it failed, because it completed everything its power source could support. But silence is not the end. There is nothing waiting in deep space to stop it. No atmosphere, no ocean, no mountain, no wall. It will continue orbiting the center of the Milky Way, alongside the Sun, for millions of years. Long after every city alive today has changed beyond recognition, New Horizons will still be traveling. A small machine, built by humans, carrying the memory of the first close visit to Pluto. So what does all of this actually add up to? At first glance, New Horizons looks like the story of a single spacecraft visiting a single distant world. But that is not really what happened. The mission changed something much larger. Before 2015, Pluto was mostly a symbol, a distant point of light, a blurry object at the edge of the solar system. Scientists had theories, computer models, careful calculations. Those are essential parts of science. But eventually, every model must face reality. New Horizons delivered that reality, and reality turned out to be far more complicated than anyone expected. The mission showed that distance does not necessarily mean inactivity. A world receiving sunlight about 1,600 times weaker than Earth can still surprise us with active geology. It showed that frozen nitrogen can slowly circulate across enormous plains. It showed that mountains of water ice can stand like bedrock in temperatures so cold that water behaves more like granite than ice. It revealed delicate blue atmospheric hazes where many expected almost nothing at all. And it demonstrated that a dwarf planet, once dismissed by many as a frozen relic, could become one of the most scientifically important worlds ever explored. That is why the title of this video is not simply about Pluto, it is about perspective. New Horizons did something Voyager never could. Not because Voyager failed. Voyager achieved exactly what it was designed to do. It transformed our understanding of Jupiter, Saturn, Uranus, and Neptune. Without Voyager, modern planetary science would look completely different. But every mission has limits. Voyager never reached Pluto. New Horizons did. And because it did, an entire category of worlds changed, from theoretical objects into real places. That difference matters. Because every time humanity finally reaches a place it has only imagined, the universe reminds us of something important. Reality is usually more interesting than our expectations. It is tempting to think this story ends at the edge of our own solar system. It does not. Astronomers have now confirmed thousands of planets orbiting other stars. Many are thought to be icy worlds. Many probably formed under conditions very different from Earth's. Some may resemble Pluto in ways we have not yet recognized. Others may surprise us completely. When scientists improve models of frozen geology, atmospheric chemistry, planet formation, or the behavior of volatile ices, those models are not used only for Pluto. They become tools for understanding countless other worlds. One successful flyby influences decades of future research. That is one reason planetary exploration matters. You cannot understand every planet by studying only Earth. You need examples. Many examples. Each new world expands the range of what nature is capable of building. Pluto expanded that range dramatically. Then Arakoth expanded it again. And somewhere beyond New Horizons' current position, countless more Kuiper Belt objects continue orbiting in darkness. Most have never been seen as anything more than tiny points of light. Some remain completely undiscovered. Researchers still cannot say exactly how many large objects remain hidden in the outer solar system. Searches continue every year. Some hypotheses suggest there could even be another large planet far beyond Neptune. Known informally as Planet 9, it has not been confirmed. Evidence remains indirect, and astronomers continue testing competing explanations. That uncertainty is important. Good science does not fill gaps with certainty. It measures, it questions, it tests. Sometimes it changes its mind. New Horizons is one reason scientists can ask those questions with greater confidence than before. There is another reason this mission matters. It represents patience. Think again about those numbers. 9 years of travel before the primary encounter. A 4.5-hour one-way radio signal. Sunlight 1,600 times weaker than at Earth. More than 15 months to return all of the flyby data. Those numbers describe a pace that feels almost impossible today. Modern life teaches us to expect instant answers, instant messages, instant downloads, instant results. Deep space exploration works differently. It rewards patience. The images that changed our understanding of Pluto were not seen seconds after they were taken. Scientists waited. Engineers waited. The public waited. Sometimes for months, sometimes for years. Every new packet of data carried another piece of a puzzle, assembled across decades. That may be one of the mission's greatest lessons. The universe does not hurry, because we do. So the next time you hear someone describe Pluto as just a dwarf planet, remember what New Horizons actually found. A world with flowing nitrogen ice, mountains built from water ice, a layered blue atmosphere, a surprisingly young surface, questions researchers are still working to answer. Then remember the numbers: 9 years, 4.5 hours. Sunlight, 1,600 times weaker than Earth. 15 months to bring the discoveries home. One spacecraft, one flyby, one chance to see a world no human eye had ever truly seen before. And even when New Horizons eventually falls silent, its journey will not end. It will continue circling the Milky Way alongside the Sun for millions of years. A silent messenger from a civilization that decided curiosity was worth the effort. Because when a spacecraft stops transmitting, the questions do not stop. Only the answers become harder to find. And somewhere beyond Pluto, beyond Arakoth, beyond every world we have explored, there are still countless objects waiting for their first close visitor. It is genuinely worth wondering what they might be hiding, too. If you enjoy documentaries grounded in real published research rather than exaggerated headlines, consider subscribing and turning on notifications. Because there is still an astonishing amount of the solar system left to explore, and we'll be here to explain it, carefully, accurately, and without the exaggeration.